Hi everyone, I'm excited to be here today. My name is Natalie Parde, and I'm an assistant professor of computer science at the University of Illinois at Chicago, where I also co-direct UIC's Natural Language Processing Laboratory. My research interests are, perhaps unsurprisingly, primarily in natural language processing, and the bulk of my work within NLP has been on different applications of multimodal NLP, as well as a lot of work that intersects with the healthcare space. Today I'm going to be talking about different ways that we can leverage multimodal patterns, so patterns from language but also other inputs, for storytelling and content analysis. Here's an overview of how my talk will be structured. I'll start out by introducing the concept of multimodal NLP in general, as well as the motivations behind addressing problems in this domain. Then I'll move on to discussions of some recent work taking place in my research group, covering some really interesting problems in visual storytelling, visual question answering, and effective analysis. Finally, I'll close by turning towards some interesting future directions for each of these tasks as they pertain to multimodal media analysis. So let's get started. Multimodal natural language processing seeks to answer the question, is language in isolation really language? And this has been an increasingly relevant topic of discussion as we increasingly often end up with these language models in NLP that are trained on huge corpora, and because they're trained on huge corpora and they're able to do an excellent job of identifying and replicating syntactic and semantic patterns, it really seems like they understand language. Some of you may have heard of GPT-2 and now GPT-3, which are both massive language models that can produce really realistic text like what you see here. On the right, we have a bunch of completions of some starter text from a recipe blog, and on the left, we have this hilarious completion of a human-written story context. All of the text completions shown here read normally enough. If I just skimmed over them at first glance, I probably wouldn't notice any major red flags. However, if you start delving into them a bit further, things start to unravel a bit. Some of the recipe completions don't really make sense from a practical standpoint, and the things they're suggesting just aren't things that a normal human would consider to be a good idea. The story is just sort of bizarre throughout, although it's quite creative. What we have here, it turns out, is a model that is very good at exploiting linguistic regularities, and honestly pretty good at exploiting semantic regularities too. However, it doesn't really understand what it's talking about. Sort of like if you go back to John Searle's Chinese room thought experiment, or more recently, Emily Bender and Alexander Kohler's undersea octopus thought experiment, where we see that it's possible for an entity to relay information without really fully engaging in communication. An interesting conclusion then from these thought experiments is that language in isolation isn't really meaningful language at all. An often heard trope is that you can't learn language from the radio, and that is in fact something that has been confirmed to some extent in child language acquisition studies. Humans learn language by grounding it in experience, and this can mean experience via sensory input, via shared understanding of user intent, via the emotions conveyed by language, or via some combination of those factors. We don't learn that a ball is round or that a box is rectangular based on dictionary definitions or word co-occurrences, but rather based on our own human perceptions associated with these words. It follows from that observation that if we want to build intelligent machines that can understand and interact with people in a way similar to what humans do, then we also need to enable those machines to learn language from experience. As a disclaimer, I'm not in any way claiming that I've done that to the degree that a human would in any of my work up until this point. What I have done, however, or at least what I hope I've done, is lay some of the groundwork for what is a very long process in getting there. A lot of my prior work focused on developing fun, interactive means through which robots could perform grounded language learning. This was motivated by the notion that it's highly unnatural to learn language from corpora, and even from multimodal corpora to some extent. When humans learn a new word, they don't scan through 50,000 images of it and extract the underlying patterns. They often learn it in one shot in the context of a natural interaction. That begs the question, why should robots rely on large corpora for their own language acquisition? I developed a human-robot guessing game similar to I Spy or 20 Questions to test the idea that robots could acquire language through natural interaction rather than through corpus-based methods. To play the game, the human first provided some short initial descriptions to the robot. For example, this is a basketball, it's round and orange, or something like that, for any objects in the playing field that were not yet known. The robot extracted concepts from the description and used its visual input to either improve upon those concepts of which it was already aware, or create new models for concepts of which it was not yet aware. It then proceeded to play a game where the human would think of one of the objects in the playing field but wouldn't tell the robot which object they had in mind. The robot would ask questions to try to narrow the playing field. For example, they'd ask things like, is it round? And if the human answered yes, the robot would increase its guessing likelihood for all of the objects that it either knew or suspected were round, based on its current knowledge of the word. Once the robot was pretty sure it knew which object the human had in mind, it would make a guess and either win or lose the game. The outcome of the game, although interesting to the human player, didn't really have any impact on the learning process. If the robot guessed correctly, it could have confirmation that the object it guessed really did or did not exhibit the characteristics that were the subjects of its questions, and could update its concept models accordingly. If it guessed incorrectly, it could similarly make adjustments to what it would realize were inaccurate assumptions. Over time, we demonstrated that the robot's knowledge of its learned concepts did improve, as measured by attribute classification tasks and guessing accuracy, and we also showed that humans had a good time playing the game. More recently, my research group has begun looking at more specific aspects of leveraging multimodal language experience to foster machine intelligence. We've asked the questions, can machines tell stories about sequences of images? Can machines generate descriptive, accurate answers to questions about images? And can machines leverage information from multiple modalities to perform effective analysis? We're still finding out a lot of these answers, and each of these questions has opened the door to some really interesting insights, which I'll share throughout this talk. So the first one of those problems I'll talk about is where we're trying to come up with ways for machines to tell stories about sequences of images. This task is generally referred to as visual storytelling. At its core, visual storytelling seeks to answer the question, given a sequence of images, similar to what is shown on the right here, can we generate a natural-sounding contextual story? It's similar but inherently different from image captioning, which seeks to provide descriptions for images in isolation. We can see a lot of those differences here. This is a hypothetical scenario with the 4 images from the previous slide. If we were to run a high-quality image captioning model on the sequence of images, we might produce captions like what you see on the left. We see that these captions nicely describe the image contents, but there's no unifying factor that ties them together. The order could be switched and nothing would need to change. What you see on the right is closer to what you would see if a human were to try to make sense of the images. The sentences are perhaps slightly less descriptive, but they build upon each other and they contextualize what is happening. We see that there's a clear narrative that flows throughout about these 2 friends going to a concert downtown. Although both tasks are challenging, the task on the right is more so because not only does the model need to understand what is going on in the image and generate a coherent description of it, it needs to understand what makes intuitive sense given what it has seen so far. In essence, it needs to be able to build a realistic story. To date, a variety of interesting approaches have been taken towards addressing the problem of visual storytelling. Most work makes use of the visual storytelling dataset, a huge collection of more than 200,000 unique images spread across more than 50,000 story sequences. Stories were acquired from crowd workers for this dataset, as were traditional image captions, both in isolation and in sequence. Named entities in the collected data were replaced with generic placeholders, but the stories were otherwise retained as is. A real example of both a story and a set of descriptions in isolation for a sequence of images from the dataset, also shown on the website in the provided link, are given in the slide here. The descriptions in isolation are on top, and the story is on the bottom. We can see that the story sentences flow together, creating a narrative, whereas the descriptions in isolation are exactly that. They tell you what is going on in the image from an objective point of view. And many interesting techniques have been investigated for generating visual stories. These techniques have included a wide range of encoder-decoder models, pipelined approaches that detect objects, make inferences from single images, and then transform those inferences into a cohesive narration, or that intelligently select photos based on the narrative being constructed, and machine translation-based approaches. We analyzed a selection of these approaches with publicly available source code, all of which have been submitted to the 2018 Visual Storytelling Challenge, to determine key areas for improvement and areas of focus that we could then adopt in our own model. Specifically, we analyzed Wang et al.'s adversarial reward learning model, Kim et al.'s global local attention cascading networks model, and Gonzalez, Rico, and Pineda's contextualized show and tell model. Wang et al.'s model, stylized as RAL, was a reinforcement learning-based approach that combined a CNN-RNN encoder-decoder policy model with a CNN-based reward model. The overall learning objective was to learn to effectively distinguish human and machine-generated stories from one another. Kim et al.'s model, stylized as GlackNet, was an encoder-decoder model with a hard attention mechanism that considered both the local image features and overall story context when generating sentences. Gonzalez, Rico, and Pineda's model was also an encoder-decoder model that made use of global context. For each of these models, we either retrained them ourselves or personally acquired the original generated stories from the model creators. We evaluated the generated stories on the basis of Meteor, Blue, Cider, and Rouge scores. Meteor calculates the alignment between machine-generated and reference hypotheses based on exact stem, synonym, and paraphrase matches between words and phrases. Blue and Rouge consider different aspects of word overlap, and Cider measures higher-level similarity between machine-generated and reference hypotheses. We examined Blue 1 through Blue 4. These different variations of Blue capture n-gram overlaps for unigrams through 4 grams. The results of our evaluation are shown in the table here. We found RL to be the highest performing model across the board, although in many cases its scores were quite close to those of contextualized show and tell. We examined the stories output by each of these models for systemic errors in an effort to diagnose key areas of focus for upcoming work. We defined stories in error to be those with Meteor scores lower than a predetermined threshold of 25. We found that stories below this threshold were of noticeably low quality. However, the threshold was generous enough that we had a sizable pool of stories to analyze. We also analyzed stories with particularly high scores, at or above a threshold of 50, to identify scoring anomalies, that is, cases where bad stories had mysteriously high scores. We made notes regarding characteristics contributing to each error, and in the process compiled a list of mechanisms by which broad categories of errors could be addressed in the future. We identified the following error categories. Grammatical errors were things like incorrect tenses or subject-verb disagreements. Contradictions were cases of inconsistent ideas within the same stories. And repetitions referred to recurrences of the same sentences within a story, the same phrases within a sentence, the same subject occurring in multiple sentences, or the same structure occurring across multiple sentences. Descriptions in isolation were sentences that were formatted more like image captions than substories, so things like, "This is a picture of X." Singular plural disagreement referred to cases where a noun was used in the singular in one sentence and plural in another. And ghost entities referred to cases where pronouns were used to refer to entities for which no prior antecedent had been introduced. Personification dealt with the attribution of human-like qualities to non-human entities. Absurdity referred to nonsensical stories, and incomplete stories referred to stories that did not contain a sentence for each image. Finally, point of view inconsistency referred to cases where the narrative point of view spontaneously changed in the midst of the story. And excessive paraphrasing referred to cases where sentences within the story were slightly different, but essentially repeated the same content over and over. Some characteristic examples of each of these error types are shown here. Notice that in many cases, underperforming stories will contain many of these error types. For example, they might contain grammatical errors, repetitions, and excessive paraphrasing all at once. We found that the most frequent error categories were repetitions and descriptions in isolation. Interestingly, both of these, as well as other error types, were most common in oral, despite oral outperforming the others. This may provide some validation for the already fairly well-known fact that automated metrics aren't perfect, especially for visual storytelling. We assume that the prevalence of repetitions in oral was likely a side effect of the model architecture. It generated sentences for the entire story in parallel rather than sequentially. This also caused it to be more likely to have contradictory sentences. We found that GlackNet stories had few repetitions, but they had a much more formulaic sentence structure than other models. This is likely due to the probabilistic sampling nature of the story decoder. We were surprised to see that contextualized show and tell had quite a few repetitions. More than 15% of all generated test stories were characterized by this to some degree, despite the model being sequential. However, it may have been that the model's strategy for incorporating global context ended up underperforming. Overall, we were also somewhat surprised to see that descriptions in isolation were one of the most common error categories, since although these existed in the visual storytelling dataset, they weren't used to train the models we analyzed. Our best guess is that the models learned that caption-like sentences were safer choices, since they were generally at least factual, if not interesting, whereas more contextual and narrative sentences were riskier. Again, reiterating the notion that automated metrics aren't perfect, we also found cases where stories received low scores but were actually pretty high quality, and cases where stories received high scores but were actually low quality. An example of each of those cases is shown here, along with the anomalous scores. And given our analysis, we decided upon the following recommendations for future work in visual storytelling. First, since we found that many of the crowdsourced training stories themselves contained grammar errors, we recommend automatically pre-processing them prior to training to reduce the prevalence of grammatical errors in generated stories. After all, a model is usually only as good as its training data. Second, since repetition was a common issue, we recommend incorporating temporal sequencing methods to increase story organization and coherence. Third, to reduce the occurrence of ghost entities or nonsensical narratives, we recommend the careful inclusion of the visual storytelling dataset's traditional image captions to see if it is possible to leverage their meaningful content while avoiding the adoption of their linguistic patterns. To this end, we also recommend the inclusion of a visual attention mechanism to facilitate visual grounding. Finally, we recommend adopting recent advances from machine translation for the visual storytelling task. Although traditional machine translation seeks to translate from text in one written language to another, at its core, visual storytelling is performing many of the same functions. The only difference is that it is translating from a visual language, so to speak, to a written one. We then applied some of these recommendations to develop our own visual storytelling model. We built our model on top of HCBNet, a model released following our earlier analysis that leveraged descriptions in isolation to facilitate the generation of its own stories. HCBNet is a hierarchical, context-based neural network, which itself is built on top of the GlackNet architecture from our analyses. We added a dynamic co-attention mechanism to HCBNet that facilitated the creation of a joint image and text embedding that focused on the most relevant aspects of both. We first encoded input image sequences using a CNN LSTM model and input text sequences using an LSTM model. This provided us with separate representations of local image features and overall theme and local context. Co-attention has previously been used in visual question answering approaches, so I'll discuss this a bit more in a few minutes when I discuss that line of our work. Given those two representations, where V is the image embedding and D is the description embedding, we compute an affinity matrix L as shown in the slide here, where W is a weight vector that is randomly initialized from a normal distribution. We normalize the matrix row-wise to obtain a set of attention weights A superscript D for the description embedding, and column-wise to obtain a set of attention weights A superscript V for the image embedding. We then map the description embedding space into the image embedding space using these weights to produce the updated context CV. This process is illustrated to the right here. Following this, we concatenated the co-attention context with the recent output of a sentence decoder, an LSTM model. The full process is shown here, where FC just represents an intermediate fully connected layer. This model formed one of my master's students' theses, so much more information is available upon request. We evaluated the model using the same automated metrics we'd included in our earlier analysis, along with a new automated evaluation metric, BERT score. We did this due to the ongoing increasing evidence that the earlier metrics are not able to capture model performance particularly well. BERT score was designed for text generation tasks like machine translation, image captioning, and text summarization, and is based on the BERT embedding similarity between candidate and reference sentences. Thus, rather than looking for simple string matches, it places more emphasis on semantic similarity. It has also been shown to be better at managing long-distance dependencies. Sure enough, we observed a discrepancy between the prior metrics and BERT score. RL still held the award for highest score with the standard metrics, but as already discussed earlier, in our manual analysis, we'd actually found a particularly large assortment of errors in these stories, while we hadn't found as many errors in GlackNet. In contrast, our model outperformed these alternatives in terms of BERT score by percentage increases of 4.5%, 24.1%, and 47.8% over RL, GlackNet, and contextualized show and tell in terms of BERT score recall, respectively. Preliminary evidence has shown that BERT score recall is most informative for image captioning tasks, and thus it was the primary focus of our analysis here. We also performed some further analyses of our model's generated stories relative to other models, and found that the stories predicted by our model contained more unique engrams than observed in other models, providing evidence that our model generates more lexically diverse stories than the alternatives. Our model also produced stories that were more in line with the reference stories in terms of length, and we found that out of all 2,000 plus stories generated by our model, only one contained repetitive sentences, and only approximately 1% of the stories contained caption-like sentences. A few sample stories output by our model are provided here. Although they're still not quite perfect, they're in general coherent, correct, and well organized. In the first example, telling a story about a sequence of wedding images, the model starts out by saying the bride and groom were ready to start their wedding. It follows by saying they took a picture of the bridesmaids, and then they danced with a couple of friends. Then it says after that they had a few drinks, and closes by saying everyone was happy to be there. In the next example, concerning a series of hiking photos, we have the story, we went on a hike to the mountains, it was a long day for a walk, we walked through the forest and then took a break. At the end of the mountain, we saw a beautiful view. So wrapping up with visual storytelling, we identified systemic challenges across a variety of publicly available visual storytelling models and made a series of recommendations for addressing these issues. We incorporated some of these recommendations in our proposed model, and of course still have room to incorporate more in future work. We introduced a novel co-attention mechanism between image and description embeddings for visual storytelling, leading to the generation of more coherent, visually grounded, cohesive, and all-around higher quality visual stories. We also experimented with a recently introduced metric, BERT score, to evaluate our stories and those generated by prior models, finding that our model achieves state-of-the-art BERT scores. In the future, we plan to experiment further with knowledge graphs and residual connections in the network to further enhance our model performance. So that wraps up my discussion of visual storytelling, and don't worry because my upcoming discussions of VQA and effective analysis are shorter. A visual question answering is the task of automatically generating answers to natural language questions about images. There's been a lot of interest in this research area lately, but to date it's generally been framed as a classification task. That means that rather than generating an answer from scratch, the model selects an existing answer class, so to speak, from a large pool of available answers. This means that models usually learn to predict short and in many cases single-word answers, making them not very similar to how a human might respond to a question. We decided to experiment with a different framework that models VQA as a fully generative task. Rather than being selected from an answer pool, answers are generated autoregressively by a multimodal language model. Our key contributions are as follows. We leveraged the recent popular transformer architecture to develop a model capable of jointly exploiting linguistic and visual knowledge, and demonstrate the feasibility of that model for our task. We then show that our novel architecture is competitive with classification-based VQA models while producing qualitatively more descriptive answers. We named our model VGG-PT2 as a function of the image encoder and language model that we used. The model employs attention mechanisms, similarly to what we did with our visual storytelling model, at multiple levels to zoom into the region of the image that contains information that is relevant to answering the question. The finer details of our model's co-attention mechanism are currently under submission, but can be provided upon request, and they were also the subject of a different master student of mine's thesis. The full architecture is illustrated here, highlighting the answer generation process beginning from a question input image pair. So we can see that the input image is encoded using VGG11, and the question and whatever has been generated thus far of the answer is encoded using GPT-2. We feed both the image and text representations to our co-attention mechanism and concatenate the output of the attention mechanism back with the text representation that was fed into the attention mechanism to generate the next word of the answer using a full linear layer followed by a softmax function. The model repeats this cycle autoregressively until the system outputs an end-of-sentence token or a maximum length threshold is reached, at which point the answer is considered to be complete. We train and evaluate our model using the VQA v2 dataset, even though this isn't quite ideal, since the VQA v2 task is very much focused on the classifier-based version of VQA. VQA v2 is a large dataset containing more than 200,000 images, 1 million questions, and 10 million ground truth answers, with an average of 5.4 questions per image. We pre-processed the data by removing grayscale training and test samples, removing short answers from the training data since we were interested in generating open-ended answers, ensuring that no more than 4 answers to the same question were used to train the model to promote answer variability, addressing minor formatting issues, and introducing beginning of sentence, end of sentence, separator, and padding tokens to the question-answer pairs to facilitate our generation process. We trained the model using teacher forcing with a cross-entropy loss and setting the language model weights to be trainable. The image encoder's weights were not trainable, so it was used solely as a visual feature extractor, but the language model weights needed to be trainable in order for the model to learn the nature of the task and the meaning of the newly introduced tokens. We trained the model for 20 epochs with a learning rate of 5 times 10 to the negative 5th power and an atom optimizer. We compared our model to 3 alternatives to tease apart the contributions of various aspects of our approach. Specifically, we compared to a high-performing image captioning baseline to assess our model's performance relative to a model that wasn't conditioned on text at all. It was just designed to produce descriptive captions of images. We compared to a question-answering baseline that was a fine-tuned GPT-2 instance that learned to answer questions exploiting the linguistic biases present in the question, which allowed us to examine how our model compared to a model trained to answer questions without being conditioned by the image itself. Finally, we compared to a high-performing publicly available VQA baseline to assess the competitiveness of our model relative to a classification-based VQA model. This model consisted of a ResNet 152 image encoder and an LSTM question encoder with a joint attention mechanism that brought those modalities into a common subspace. The attention output was concatenated back with the LSTM output, and the resulting vector was fed to a classifier, which distributed probabilities over 3,000 possible answers. So in many ways, this model was somewhat similar to ours. However, it was classifier-driven rather than taking an autoregressive language modeling approach. We evaluated our model using accuracy to facilitate comparison with prior VQA work. However, this was a very suboptimal metric for us to use because since our model was generative, there were many cases where it would generate a semantically similar but lexically slightly different answer from the gold standard and therefore be considered inaccurate. Because of this issue, we also evaluated our model's performance using BLEU1 through BLEU4 and word movers distance, which exploits pre-trained word embeddings to assess semantic similarity. In terms of accuracy, our model surprisingly performed competitively to the VQA baseline, actually surpassing its accuracy with yes/no answers. This was particularly surprising given that we didn't even use any one-word answers to train our model. So it appears that when our model went against its training instincts to output a very short answer, its predictions were highly likely to be accurate. For other answers, the VQA baseline performed better than VGGPT2, but again, this is to be expected given that the VQA baseline was classification-based, whereas our approach produced unconstrained free-form answers. In terms of BLEU score, comparing each model's output with its respective 10 ground truth answers from the VQA V2 corpus, we found that our model performed much better than the VQA baseline, as well as other alternatives, with respect to the quality of its longer answers. This provides further validation to the argument that the VQA baseline performs well with single-word answers, but its performance diminishes as answers become more descriptive. As with accuracy, both VQA models also outperformed the captioning and answering baselines, confirming that multimodality is key to producing high-quality answers. Finally, in terms of word movers distance, we found that our model produced answers that were highly competitive with those produced by the classification-based VQA approach in terms of semantic similarity with the reference answers. Thus, this supports the notion that an open-ended generative architecture offers a feasible alternative to traditional means of addressing the VQA task. Although there isn't much time to delve into a qualitative analysis of the answers produced, this slide shows some sample questions and answers produced by both the VQA baseline and VGGPT2 for comparison purposes. We see that the answers produced by VGGPT2 are more descriptive than those produced by the VQA baseline, while also remaining more accurate. We also visualize a few of our attention maps here, demonstrating the ability of the model to identify salient aspects of the images in order to answer questions correctly. In conclusion, in this work we proposed a transformer-based generative model for visual question answering to produce unconstrained descriptive answers. We verified the feasibility of the approach and demonstrated that it performs competitively with the classification-based VQA model. In the future, we plan to experiment with deeper image encoders and a multi-head variation of our attention mechanism to see if this can further improve model quality. So that wraps up my discussion of VQA. I'll just very briefly touch upon some new work one of the PhD students in my group is investigating with respect to multimodal effective analysis, before also very briefly describing some interesting future directions. Effective analysis is the task of automatically determining the emotions or sentiments evoked by an input image or text sample. For example, an image of a birthday cupcake might evoke feelings of happiness, whereas a really negative paper review might evoke feelings of anger or sadness. Traditionally, automated techniques for effective analysis have relied on information matching their input modality. Visual features have been used to assess effective content of images, and text features have been used to assess effective content of language. However, handling effective analysis this way fails to capture a lot of supplemental information that may be quite useful. Our experiences in life aren't naturally unimodal, even with respect to squarely unimodal tasks. Why should our computer's experiences be? An interesting new direction our research group is pursuing is the use of multimodal techniques to solve unimodal effective analysis tasks. Specifically, we're interested in exploring whether useful biases latent in word embeddings can be used to improve performance in effective image analysis. For example, traditional effective image analysis might look at the image here, and it might decide, okay, we have some bright yellow and blue. We have this item that commonly appears in pictures labeled as happy. We have a lot of color saturation. This is probably an image that would evoke happiness. These are all interesting and probably quite relevant things to consider, and would likely play a role in how a human felt when looking at the image. However, a human's emotions might also be influenced by other thoughts that are stirred from looking at the image, even though there's no visual record of them. A human might think, oh, this is a cupcake with fun sprinkles and a little yellow candle sticking out of it. This means that it's probably a birthday cupcake, and birthdays are happy, and now I feel happy looking at this image. Especially for the really abstract terms in that process, word embeddings could be the missing piece of the semantic network needed to encode this thought process. To date, we've performed some preliminary experiments investigating this hypothesis, with initial results supporting the idea that the inclusion of word embeddings associated with identified concepts from images leads to a slight but measurable performance boost. Currently, we're working on fine-tuning these techniques and identifying optimal ways to fuse linguistic information with our visual inputs. So this brings me to my conclusion. Given all we've seen today and the current state of these fields in general, what are some interesting future directions that we can pursue? We saw with visual storytelling that sequential models are important for generating sensible, coherent narratives. And furthermore, co-attention mechanisms are important for facilitating visual grounding. That is, making sure that the story not only makes sense on paper, but makes sense given the images that go along with it. However, there are still several important open problems, including some which were unearthed by our earlier analysis. Generated stories often suffer from a lack of narrative creativity and can sound formulaic at times. Grammatical issues also still persist. We recommend the future work in this area tackle these issues, perhaps through the adaptation of recent advances in the somewhat parallel field of machine translation. We saw with visual question answering that a generative autoregressive model can perform competitively with classical VQA approaches, while potentially opening the door to more natural descriptive answers. However, the best way to generate these unconstrained answers remains to be seen, and new evaluation paradigms are likely needed to more appropriately quantify these advances. Finally, we saw with effective analysis that current approaches may be missing out on potentially valuable information from seemingly irrelevant modalities. However, many open questions remain as to how to best combine latent biases from supplemental modalities. Really, in order to perform full human-like multimodal media analysis, we may need to develop systems that capture properties of each of these tasks. After all, being able to effectively tell stories about image sequences inherently relies on an ability to accurately answer questions about those images and to understand the emotions that they evoke. At their core, these and other multimodal tasks are closely intertwined. I'm excited to see what further advances in these fields are soon to come.